stuff. I had you on your calculators, I had you actually typing these in and figuring out what was happening as you let n get bigger and bigger and bigger. This says if you let n be numbers that are getting bigger and bigger and bigger, approaching infinity, like 1,000 and 2 million and 3 billion, what is happening to this fraction? Well, in most cases, the fraction is heading towards something. Not always, but in most cases, it's heading towards something. In other words, if you were to plot, you let n be 10, and then let n be 20, and then let n be 100, and let n be 1,000. As you plotted those on a number line, they would be heading toward a number called the limit. They'd be getting closer and closer and closer to that number. Now, those of you that did the exploration and paid attention to the homework paper that I gave you, know that in an expression like this, as n gets bigger and bigger and bigger, these numbers become less significant. Now think about that for a minute. If we're letting n be 1,000,000, how important is the 4? It's not. And the -6, it's not. If you're letting n be 1,000,000, you basically have 5 million over 3 million, which reduces to 5/3. So the limit of this is 5/3. And it will work like that every time you have n's over n's. So when I look at, let me find another one like that. That's the answer. So now I'm going to skip down to number 9. Okay? Now when I get to number 9, now think about letting n be a huge, huge number, like 1,000,000. If you put 1,000,000 in here for n, how significant is 1? Not at all. How significant is 3? Not at all. So what do we basically have? -2 million over 6 million, which reduces to what? -1/3. So the limit is -1/3. Now, take a look at number 8, because it is exactly the same thing, except there are 2 of them. No big deal. We're going to find the limit of each one individually, and then we'll multiply them together. So what is the limit of the first expression? 1/2. Okay, so the limit of this one is 1/2. Again, we're talking about n getting huge, like 1 billion. 1 and -3 do not count when you're talking about 1 billion. This is basically 1/2. Now, will it ever actually equal 1/2? No, that's not what we're saying. We're saying it's going to get closer and closer to 1/2. Now, what about this one? What's this one doing? Getting closer and closer to 3/2. So what's the answer to the question? 3/4. Now, take a look at number 4, because it's kind of the same thing, except it's got, you can handle the second part of it. What's the limit of the second part in number 4?
3.
Watch the signs there. I think it's -3, isn't it? Won't that limit be -3? Now, there are really 3 rules that we're going to talk about with limits. One of them, all these problems are one of them. But this is a different thing, because this doesn't even have any n's in it, right? This would be if you thought of it as a sequence, this would be a sequence that's all 5s. It's just 5. So the limit of it is 5. When you have a constant, when you have no n's in the problem, just a number, the limit of that is just that number. So the limit of 5 is just 5. So the limit of this is 5. The limit of this is -3. What am I supposed to be doing with those two numbers? Adding them together, so the answer to the problem is 2. Now look down at number 11. What's the answer to number 11? 18. The limit of a constant is just that constant. And when I say constant, I mean just a number. There's no n's anywhere in it. It's just the number. So the limit of 18 is 18. Now, we got a few variations here to talk about. Let's look at number 2. And then we have one more rule to learn too. There's something you have to be careful about in this one. Does anybody want to hazard a guess what the limit of this is? It's 0. And the reason the limit is 0 is this. I want you to think about letting n, remember, it's getting bigger and bigger and bigger. Let n be 1 billion. What is the most powerful term, or what term is the biggest in the numerator if you let n be 1 billion? 2n squared. And it would be really big, wouldn't it? Okay, let's look at the denominator. What's the biggest or most powerful term in the denominator? 3n cubed. Now wait a minute. Will 2n squared ever keep up with 3n cubed? No. So as we go farther down the line, letting n get bigger and bigger, going from 1 billion to 2 billion to 1 trillion, what's going to keep happening to the denominator? It's going to keep getting bigger and bigger and bigger and outweighing the numerator. Now, is the numerator going to get big? Absolutely. But it's not going to get as big as fast as the denominator is. Do you understand me? So what happens to a fraction when the denominator is getting bigger than the numerator? The fraction is getting smaller. Anytime your power on the bottom is bigger, your fraction's going to be bottom heavy. Agreed? Mm-hmm. And anytime you have a bottom heavy fraction, it's going to be getting it's going to be getting smaller, which means it's going to be getting closer and closer to 0. So it doesn't matter what the powers are. If we had 3n minus 1 over 5n squared plus 2n plus 8, that would still be 0. Because the power on the bottom is bigger, and it's always going to outweigh the top. Now, take a look at number 6. So the answer to number 2 is 0.
0, 6, 1.
And the answer to number 6 is actually no limit. It does not have a limit. Now, would somebody like to try to explain why number 6 has no limit? Now, think about the argument we just made for why this was 0. Why did we say that was 0? The denominator was outpacing the numerator, right? So I want you to look at number 6 and tell me, think about putting in 1 million. What's going to happen to this fraction? The numerator is exploding, right? Is the numerator outpacing the denominator? Yes. Okay, now wait a minute. What happens in a fraction when the numerator gets bigger and bigger and bigger, the fraction just keeps getting larger, right? So on our number line, remember that picture I drew that said we had, we're trying to find what that fraction approaches? Well, wait a minute. If the fraction is just getting bigger and bigger and bigger and bigger and bigger, is it approaching anything? No. Okay, so when we have these fractional expressions with n's over n's, if the n's match in power, if they're the same power, then the limit is just the ratio there, right? If the denominator is the big one, if they don't match, if the powers don't match, and the denominator is the biggest, then the limit is always going to be 0. If they don't match, here you have n's in the top, you don't even have any n's in the bottom. If they don't match each other, but the biggest power is on the top, then there is no limit. Now, does that make sense to you? I know you can memorize it, but does it make sense to you? Think about the fractions. If the top is bigger, you're just getting bigger. If the bottom is bigger, you are getting smaller. Robert?
So the whole point of it is like the limit is what it'll eventually reach, or like.
Well, it never gets there usually. I mean, once in a while it does, but it's getting closer and closer to that.
Okay.
Now, this one has radicals in it. This is number 7. Do not freak out. Think about putting in a million or something. Up here, you're going to take the square root of a million. Here, you're going to take 2 times the square root of a million. The limit's 1/2. These 2 powers are exactly the same, so the ratio is 1/2. Okay? That was easy enough. All right, now, all of the rest of the problems, let's see, what is it, 3, 5, and 10, they are all different. 3, 5, and 10 are different than what we've been talking about. Do you see that? 3, 5, and 10 are fractions raised to powers. Now, let me tell you right now that the power is not important. So nothing's going to change if that's an n minus 3, a 6n, a 12n minus 5. The power is not the important thing. The important thing is, I want you to stop and think about what happens. This is number 3. If you take 3/4 and raise it to higher and higher powers. So you take 3/4 times 3/4 times 3/4 times 3/4. What happens to your answer as you raise it to higher and higher powers? It gets smaller, doesn't it? And as it gets smaller and smaller and smaller, think about that number line. What are we heading toward if it's getting smaller and smaller and smaller? 0. So the limit of this is going to be 0. Now, would it have made any difference if that would have been 2/3 to the 5n plus 6? None. We are still multiplying 2/3 times 2/3 times 2/3, and those fractions are getting smaller and smaller. I had you do that in your homework, those of you that did it, and you know that problem where I forget what this number was, but you raised it to a high power and it got really tiny. Very tiny. Jamie?
Can it be a fraction?
No. We're talking, I didn't make that connection. We're talking about these being terms of a sequence, so n is a whole number. Yeah, n is a whole number. Now look at this one. What's happening here with this one? Now this time we're multiplying 5/4 times 5/4 times 5/4. Now be careful. What happens when we multiply 5/4 times 5/4 times 5/4?
No limit.
There is no limit, because why?
It's just gonna keep getting bigger.
It's just gonna keep on getting bigger. You are multiplying by a number bigger than 1. Doesn't that make your answer bigger? It's like timesing by 2 or 3. It just keeps getting bigger and bigger and bigger and bigger. What about this one? No limit. What's the key here? These problems that are simply something raised to a power, they look different than these, okay? The ones that are something raised to a power, what's the key? If the fraction is greater than 1 or less than 1. If the fraction is greater than 1, there will never be a limit. If the fraction is less than 1, the limit will always be 0. Okay, now turn it over, and we have, this is an actual quiz. Okay, so let's look at number 1. Evaluate the following limits. All right, pay attention to problem A. What is the most powerful term on the top? 3n squared. What's the most powerful term on the bottom? Negative n squared. Oh, they match. So what's the limit? Negative 3. It's 3 over negative 1. Negative 3. All right, what about B? 0. Now, I know that there's a negative in there. That doesn't change anything. All it means is you'd be flipping back and forth between positive and negative, but every term would be getting smaller. It would be heading toward 0. All right, now be careful with C. 0. Why is the limit 0 for C? The power on the bottom is bigger. So that means the fraction is bottom heavy. And when the fraction is bottom heavy, it's small. What about D? No limit. Why? The fraction is bigger than 1. Everybody okay with those problems? Okay. Now, number 2, these are our actual problems. So, when we do these problems, what are the 2 questions that we ask ourselves? What's the first thing we have to figure out? Is it arithmetic or geometric? So we look at it, here we go, we got 5, and, oh wait, these things 1, got 1, and then 5, and then 9. Okay, so what have we got here? Arithmetic. What's the second question that we always have to decide? We have 2 arithmetic formulas, right? And you have to decide which of these you are going to use. And how do you make that determination? Am I looking for just another number in the list, where I would use this formula for that? Or do I want to add all those up? I would use this formula. Right? So what does it say? If this pattern continues, how many songs will he sing after the 100th trip?
That's add and C.
Boy, that's not a very well worded question. I will do better next time. If this pattern continues, how many songs will he sing, let me say, on the 100th trip?
Oh, so that's...
So on the 100th trip would be this one. So that would be A sub 100 equals 1 plus 4 times 99. So 397, if my arithmetic is right. Now the question could also have said, if this pattern continues, how many songs will he have sung after the 100th trip? That would very clearly mean add them up, right? So I have to do a better job with my grammar. So if it said, how many songs will he have sung after the 100th trip, you would say S sub 100 equals 100 over 2 times what? 1 plus 397. So if I had asked that question, you would still need to do this, right? We've talked about that before. This formula requires you to have the last term. If you don't have it, you have to find it. Okay, number 3. If you need 3 M&Ms on the first day, 6 on the second day, 12 on the so that's 3, 6, 12. How many will you eat on the 14th day? All right, is it arithmetic or geometric?
Geometric.
It's geometric. You have 2 geometric formulas, which I'm going to give you all these formulas. So you have to decide which one you're going to use. There's no confusion. How many will you eat on the 14th day? That's this one right here, right? Because this is how many I ate on the first day. This is how many I ate on the second day, the third day. I want to know how many I'm going to eat on the 14th day. So that would be A sub 14 equals what? 3 times 2 to the 13th. And we type it in our calculator and we probably get some big giant number. And then the last question says, okay, I got a sequence here that apparently is geometric because it says, what's the ratio? So in other words, what am I multiplying by to get from term to term? 3/4. That was kind of easy. All right, now let's get our homework papers out. Now that we've gone through all that, this should be a breeze. Okay, so we had 3 kills in the first game, 8 in the second, 13, and so on. How many kills did she have all together in her first 10 games? All right, arithmetic or geometric? Arithmetic. Am I looking for a number in the list, or do I want to add all those up? Add them all up. So the formula for an arithmetic sum is this. So here we go. I want to add up how many games? 10? So that's 10 over 2. Her first game was 3. Oh, shooty tooty. This is another example. What goes here? The 10th game, which I don't know. So over to the side, I'll do the 10th game. And the 10th game, that formula is this. So the 10th game will be 3 plus 5 times 9. So that's 48. That's the number that goes here. So I've got, is it 255? As the answer to the question. Oh, it wasn't in that pile of stuff I gave you?
No.
Okay, go back and get one. They should be back there in the first column. If not, you have to take a picture of somebody. Okay, now, number 2. How much money would be on a checkerboard if we put 30 cents, 90 cents, 270, and so on? How much money would be on the checkerboard? Okay. All right, now what is this? This is geometric, and I want to know how much money would be on the checkerboard. So am I looking for a term or a sum? Sum. How much is on the board altogether, right? So the formula for that is this one. So here we go. We're adding up. I told you the other day, and now I expect you to know there's 64 squares on the checkerboard. First term is 30. What's my ratio?
3.
3. I'm multiplying by 3. This is going to be a huge number. That's negative 2. This is going to be an absolutely huge number. Remember, when there's an E, that's scientific notation. And there will definitely be an E. Okay, so I got 5.15 times 10 to the 31st. What's the unit on that? Cents. Now when we talk about, think about econ, when you talk about like the national debt and the gross national product and all that stuff, do you ever talk about it in cents?
No.
No. So we're going to change this to dollars. So that would be 5.15 times 10 to the $29. Because when you go from cents to dollars, you divide by 100, right? Or move the decimal point 2 places. It's still a huge number. All right, Alyssa smiled twice, 6 times, 18 times, and so on. How many times did she smile on the last day of May? All right, so what are the questions we go through? Arithmetic or geometric? What have we got? Geometric. Are we looking for a number in this list, or are we looking to add all those up? We want a number in the list. How many days are in May? 31. So we want the 31st term. And the formula for that, geometric sequence. So we'll take 2 times 3 to the 30th. And it's a huge number. You're going to get E again. You're going to get scientific notation. And that's how many smiles she had on the last day of May. All right, now let's turn it over and do the limit problems now that we've talked about these. I know I left tons of space. You don't need any space. If you know what's going on, if you paid attention at the beginning of the period, you can just write the answers. There's no work to show. What's the limit for number 1? 0. Why is the limit 0? Because 2/5 is less than 1. And when we have a number raised to a power, the limit is either 0 or there is no limit, depending on the size of the number you're raising. All right, what's number 2? 4/5. What's number 3? No limit. Number 4? 6. Number 5? 3/5. And number 6? 6. The limit of a constant is always that constant. Okay? All right, let me just throw a couple more limit questions up here just to make sure those tricky ones you've got figured out. So if we had what would that limit be?
0.
Why? You're right. Why is it 0? Because the bottom is bigger. The power on the bottom is bigger. Good. What about this one? What would that one be? 3 plus 2/3, 4/6, 2/3. So 3 2/3 or 11/3. Everybody okay with that? All right, one more. What's the limit of that one?
No limit.
No limit. Why? You're right. Why? The top is bigger than the bottom. And when you have a fraction that's top heavy, the answer, if you typed it in on your calculator, is just going to get bigger and bigger and bigger if the top is growing faster than the bottom. Robert?
Will it ever be like limit? Like, will it ever be something other than n approaches infinity?
No. Well, yes, it can be, but not for us.
Okay.
All our n's are approaching infinity. But yes, there are. You will do in your calculus class. You will do limits of n approaching other things. All right. So tomorrow we have a quiz over kind of like this. It's some limits and some problems where you have to do arithmetic sequences and series. So we've got a few minutes. Are there any kinds of sequence and series problems that we need to practice? I will give you the 4 formulas.
That's what I was gonna ask.
Dan, what are you doing? Not in math class. Jeannie is a wonderful person, but not in math class. All right, Zach, what was your question?
I was gonna ask if you were gonna give us the formula.
Yes, I've said that since the beginning. I'm going to give you the formulas. Your homework is to study. So I have given you over the last few days some practice quizzes, some practice sheets. We've gone through those. You've got these. That's your homework.
Wait, do we have a quiz on this one?
We have a quiz on it tomorrow. And what was the first term? I don't know the ratio, but it's the 6th term. So I divide by
everything's included, like internet,
I don't worry.
I remember one problem, guys, listen, remember those problems where it said, is, I don't know, is 2016 a term of the sequence 4, 10, 16, da 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 da. Remember those? Let's think about that for a minute. First of all, what kind of a sequence is that? It's arithmetic. So the term formula would be this. So 2016 would have to be the n term, right? And that would be 4 plus 6 times n minus 1. Now, what's the key? That is always going to be solvable. You're always going to get an answer. But n has to be a whole number. You can't have, the question is that a term? Which means it would be the 10th term. It won't be the 10.3 term, right? So when you solve that equation, you have to come up with a whole number. If you don't, if you get a fraction or a decimal or a remainder or something like that, then you know it is not a term of the sequence. Remember that? Okay, Sarah?
You don't fill it in the end because it's like you're not saying a specific term.
You don't know what term, n is the number of term it is, like the 5th term. You don't know what term it is.
Okay, yeah.
And besides, Sarah, that's the only variable. I mean, you gotta have a variable in your enclosure strip. That's the only thing I don't know. Alright? Remember vocabulary, what's the common ratio?
With a geometric.
The common ratio is the number that you multiply by in a geometric sequence. What's the common difference?
Number you add.
The number you add, right, in this case, it would be 6, that's why we put 6 in for D. When do you use the A sub n formulas? You have 2 A sub n's and 2 S sub n's. When do you use the A sub n's? When you're interested in a number in the list. When do you use the S sub n's? When you want to add them all up. You should be familiar with how many squares there are on a checkerboard, with how many days there are in the various months.
I don't know that one.
It goes like 31, 28. Wait, I don't know.
No, March
There
is
are 30 days in September, April, June, and November. All the rest have 31 except for February. So there are 30 days in April, June, September, and November. No, yeah. No. 30 days, that's September, April, June, and
Just have 30 days now.
all I need to do, if I can just figure out something.
Okay, all right.
I'll be so
People who got